Every reef tank looks simple on the surface. Some fish, some coral, some rock, some lights. But the deeper you go into this hobby, the more you realize there are layers of knowledge most people never reach, from basic biology to advanced systems to things so niche that only a handful of hobbyists have ever tried them successfully. Welcome back to the Reef Manual. Normally, we move through this series chapter by chapter. In the last video, we talked about the nitrogen cycle, and we said the next chapter would cover what happens after the cycle is complete and how to add livestock safely. That chapter is still coming. But before we continue, this video is a pause, a step back to look at reef keeping as a whole. From the knowledge everyone starts with to the strange, advanced, and experimental corners of the hobby that most people never see. This is the reef-keeping iceberg. The tip of the iceberg. This is universal knowledge. Saltwater fish are colorful and territorial. Marine fish are known for bright coloration, which is used for communication, camouflage, and mating. Fish like clownfish, chromis, royal gammas, and dwarf angelfish are often chosen because they look vibrant even in small tanks. What beginners quickly learn is that many saltwater fish establish territories, especially around rockwork. A clownfish may claim a corner of the tank, while a dottyback might aggressively defend a cave. These behaviors are normal, but they require planning when selecting tank size and tank mates. Corals require light for photosynthesis. Most reef corals rely on symbiotic algae called zooxanthellae that live inside their tissue. These algae use light to produce energy, which the coral then consumes. Corals such as Montipora, Acropora, and bird's nest require strong, stable lighting to survive long term. Others, like mushrooms and zoanthids, tolerate lower light but still depend on it. Without appropriate lighting, corals lose color, stop growing, and may eventually die. Live rock provides filtration and habitat. Live rock is one of the most important components of a saltwater aquarium. Its porous structure provides surface area for beneficial bacteria that process ammonia and nitrite. It also houses worms, copepods, amphipods, sponges, and other microfauna. Fish use live rock for shelter, sleeping, and territorial boundaries. While many beginners place rock for aesthetics, its biological function is what allows the system to support life. Invertebrates are sensitive indicators. Invertebrates such as snails, shrimp, crabs, and starfish react quickly to changes in water chemistry. Sudden salinity swings, ammonia spikes, or temperature drops often affect them before fish show symptoms. For example, snails falling off of glass or shrimp hiding constantly can indicate stress. Because they lack the resilience of fish, invertebrates often act as early warning systems. Observing their behavior can prevent larger problems later. Just below the surface. This is basic hobby knowledge. The nitrogen cycle. The nitrogen cycle describes how waste is processed in a saltwater aquarium. Fish waste and uneaten food break down into ammonia, which is toxic. Beneficial bacteria convert ammonia into nitrite and then into nitrate. While cycling establishes these bacteria, the process never truly ends. Each new fish, feeding increase, or bioload change forces the system to adapt. Not all fish are reef safe. Not every saltwater fish can live safely with corals or invertebrates. Some species, such as certain angelfish, butterfly fish, or triggerfish, may nip coral polyps or eat shrimp and snails. A foxface rabbitfish may ignore corals for years, then suddenly develop a taste for soft corals. Compatibility depends on species, individual behavior, and tank size. Researching fish behavior before purchase prevents long-term issues. Hard corals consume calcium, alkalinity, and magnesium. Stony corals build skeletons from calcium carbonate, which requires calcium, alkalinity, and magnesium. Species such as Acropora, Montipora, Chalices, and Euphyllia consume these elements at different rates. As corals grow, demand increases, requiring testing and supplementation. If levels swing too quickly, corals may stop growing or lose tissue. Stability matters more than chasing perfect numbers. Feeding is critical for invertebrates and corals. Many reef organisms rely on more than leftover food fish. Filter feeders like feather duster worms, sponges, and some LPS corals require particulate food in the water. Even photosynthetic coral benefit from supplemental feeding. Tanks that appear clean and algae-free can still be nutritionally deficient. Feeding appropriately supports growth and long-term health. Mid-iceberg. This is experienced hobby knowledge. Mandarin dragonets require sustained microfauna. Mandarin dragonets feed almost exclusively on copepods and amphipods. They pick constantly throughout the day and rarely accept prepared food. Successful long-term care requires a mature tank with abundant live rock and established microfauna. Many keepers support mandarins using refugiums that constantly breed pods. Without this, mandarins slowly starve despite appearing healthy. Deep sandbeds create layered biology. Deep sandbeds, typically over 10 or 15 centimeters, develop oxygen-poor zones. These zones support bacteria that reduce nitrate into nitrogen gas. The sand also hosts worms, crustaceans, and microorganisms that recycle waste. Disturbing deep layers can release hydrogen sulfide or trapped nutrients. For this reason, deep sandbeds must be intentionally designed and left undisturbed. Kalkwasser dosing. Kalkwasser is a calcium hydroxide solution used to supply calcium and alkalinity. It is often added slowly through top-off systems to maintain stability. Kalkwasser also raises pH, which can benefit systems prone to low pH. Overdosing can cause rapid pH spikes that stress or kill livestock. Proper dosing requires testing and controlled delivery. Species-focused coral systems. Some aquarists choose to keep tanks dominated by a single coral group. Examples include Acropora-dominated SPS tanks or Euphyllia-dominated LPS tanks. This approach reduces chemical warfare between coral types. It also allows lighting and flow to be optimized for specific species. However, mistakes affect the entire system, making precision critical. Coral aggression and space competition. Corals compete for space using physical and chemical methods. Some extend sweeper tentacles at night that sting neighboring corals. Others release toxins into the water or grow over competitors. Placing corals too close often leads to tissue loss. Proper spacing and long-term planning prevent these conflicts. Deep iceberg. This is advanced and obscure knowledge. Sharks and predatory fish in large systems. Certain sharks and large predatory fish can survive in captivity under specific conditions. Bamboo sharks and epaulet sharks require wide tanks with large footprints and high oxygen levels. These animals are sensitive to poor flow and improper diets. Most failures occur because tanks are too small or poorly designed. Successful systems resemble swimming pools more than aquariums. Cephalopod aquariums. Octopuses and cuttlefish are intelligent, problem-solving animals. They require sealed tanks, live food, and environmental enrichment. Many species can open lids, unplug equipment, or escape through small gaps. Their short lifespans also mean emotional investment with limited time. These systems fail when keepers underestimate behavioral complexity. Mangrove aquariums. Mangrove systems integrate terrestrial plants into marine tanks. Their roots provide habitat for copepods, worms, and juvenile fish. Mangroves absorb nutrients slowly and requires years to mature. Lighting must support leaf growth above the tank. These systems reward patience rather than rapid results. Rare or protected species. Some reef species are no longer collected from the wild. Others exist only in captivity through propagation programs. Maintaining these animals requires careful sourcing and record keeping. Losing one may mean it cannot be replaced. These systems emphasize conservation over display. Plankton-driven reef systems. Some advanced aquarists rely on live plankton as their primary food source. Continuous cultures feed corals, filter feeders, and small fish. These systems require careful balance to prevent crashes. Population collapse can starve the tank quickly. When successful, they closely resemble natural reef food webs. The abyss. This is extremely niche techniques. Mesophotic reef species. Mesophotic corals come from deep reefs with low light. They require stable parameters and gentle flow. Growth is extremely slow, sometimes measured in millimeters per year. These corals fail under standard reef lighting. Replicating deep reef conditions is technically demanding. Microfauna ecosystem reactors. Some aquarists maintain dedicated systems to culture copepods, amphipods, and worms. These reactors feed demanding fish and corals. Balance between reproduction and predation is critical. A crash can eliminate food supply overnight. These systems require constant monitoring. Spawning manipulation. Captive spawning is achieved by simulating lunar cycles, temperature changes, and seasonal cues. Successful spawns have been documented in clownfish, dottybacks, and some corals. Timing errors result in failure. Even successful spawns often produce few surviving offspring. Cryptic invertebrate zones. Dark zones house sponges, tunicates, and worms. These organisms filter water and recycle nutrients. They are rarely visible but play major biological roles. Creating cryptic zones requires low light and moderate flow. These areas mimic reef caves. Coralline algae diversity. Coralline algae includes many species with different requirements. Some prefer high light, others thrive in shaded areas. They influence calcium consumption and microbial settlement. Color alone does not indicate health. Understanding coralline diversity improves long-term stability. Final depth. These are experimental practices. Azooxanthellate corals, bioluminescent plankton systems, sponge-only microcosms, symbiotic pairings, and microbiome manipulation represent the edge of reef keeping. These systems are fragile, unpredictable, and often undocumented. Success depends on deep biological understanding. Failure is common. At this depth, reef keeping becomes experimentation. This video was a pause. not a detour. In the next chapter of the Reef Manual, we'll cover what happens after the cycle is complete, how to add livestock safely, and how to avoid common early mistakes. If you enjoyed this breakdown, make sure to like the video, subscribe to the channel, and leave a comment letting us know which part of the iceberg surprised you the most.